Okay, let's continue. Example 3 is understand stretches and compressions. Part A, graph f of x equals absolute value x with domain -4 to positive 4. And g of x is equal to 2 times f of x. How are the domains and ranges related? So first, we can look at the table of values, right? So for all x from -4 to 4, of course, the decimals and fractions in between are also included, but to graph it easily, we're just going to choose integers, right? From -4 to 4. So -4, and you can also skip a little bit just to graph the overall shape, right? -2, 0, 2, and 4. Those are the domain that we have. We're inside the domain, right? Just pick some points that will help you graph. And then f of x will be just absolute value of x. So if you make all of these x values positive, that's your y values, right? So as you can see, the blue graph will be your f. That is your normal graph. And then you have a transformation. What if you multiply 2 to the entire function? So you're multiplying 2 to f of x, not x, okay? So your f of x is 4 when x is -4. So if you multiply 2, it's 8. So when x is -2, in the same way, y is 4 in g of x. 0, 0, 2, 4, 4, 8 is your new points. So if you graph them, you will have a new graph. And it also stays in the domain that we had. So the domains are the same, but each of the y value is multiplied by 2. So you can see that the graph actually stretched by 2 vertically. So this is called a stretch. Stretch is another type of transformation. When describing stretch, you will typically say the scale factor as well. So it's a vertical stretch. So you need to say if it's a horizontal or vertical stretch of the graph of f by a factor of blank 2. Okay? So that is an example of a stretch of an absolute value function. Let's look at another example of stretch or compression. So what if you are not stretching? What if it actually gets smaller, right? So let's look at part B. So we're using the same function, f of x is equal to absolute value x, same domain, -4 to 4. But now our h of x is equal to f of 2x. Okay, so now we can see that we're multiplying 2 to x. And then we are getting our function, right? So look at -2, -1, 0, 1, 2. Our domain, we're picking smaller domain because later your values will tell you if it's positive or not. So let's first look at these y values. That is your normal y values, right? Original y value, 2, 1, 0, 1, 2. But then your x is going to be multiplied by 2. So -2 times 2 is -4, right? That is actually our end of our domain, our beginning of our domain. So if your x is greater than or less than -2, it actually doesn't fit the domain. So that is not going to exist in this situation, okay? Because our original domain is -4 to 4. So now your domain for h of x will be reduced to -2 to 2. So when we have a horizontal compression, our domain will also change. If we had a restricted domain, our restricted domain will change, okay? So if you multiply -2 by 2, that is -4, right? So f of -4, you plug in -4 inside the absolute value, will be +4. So it's a positive 4. Negative 2 comma positive 4, and then the same way, negative 1 comma 2, and then 0 comma 0, 1 comma 1, 1 comma 1, and then 1 comma 2, and then 2 comma 4. So your new graph is a much smaller graph than the original graph. Okay, so this is called a compression. So horizontally, if it compresses, it gets closer to the y-axis, okay, because it's compressing horizontally. If it's compressing vertically, it gets closer to the x-axis, okay, or this way. Yeah, it doesn't always have to be the x-axis or the y-axis. It only works when your vertex is exactly on the x or y-axis. So it just moves in the opposite directions. Okay. Let's look at try number 3. Show that j of x is equal to f of 1 over 2x is a horizontal stretch of the graph of f. So you know this is horizontal, right? This is horizontal stretch because it's inside the function. We're just multiplying 1 over 2 by x, but this is a stretch. So for horizontal, if you're multiplying to the x, that is a compression. You see that? Visually, it compresses. Why? Because if your x is less for the same values of y, that means you have a wider stretch. But then if your x are bigger than the same values of y compared to the original function, then that means it's smaller. You're compressing. Okay? So yeah. So explain. So show how this is a stretch. You should probably graph. Okay, pause the video, go graph again, and come back when you can show me why. Okay, are you ready? So when you graphed it, your original absolute value should look like each slope has a slope of -1 and 1, right? But if you graph this one, f of 1 over 2x, right? Then you have 1 over 2, 1 over 2x, and then absolute value, right? So then, if your domain is -4 to 4, how big can your x become when you can graph from -4 to 4 ultimately? So how big can you plug in numbers for x? So you can plug in numbers from -8 to 8, right? Because -8 divided by 2 will be -4, and that fits into our original domain. And +8 divided by 2 is 4, again, and that also fits into our domain. So your table should be from -8 to +8 for x. And then your y values are going to be staying the same for lesser and bigger x's. So this should be your graph. This should be about how your graph should look like. So if your domain, so if your domain has an endpoint, it's restricted, your domain will change because this is a horizontal stretch. And if your domain stretches, that means you have more distance, more range of the domain, right? If you divide it by 2. So if domain is stretched, that means you have a horizontal stretch of the graph. So we can say for any graph, if A comma B is the domain of x, or of j of x, then j of a, so if you plug in the end value for this one, j of a should be f of 1/2 a. And okay, does that make sense? And j of b, so the bigger value of the restricted domain is equal to f of 1/2b, right? So that means 1/2a, comma 1/2b I'm just putting parentheses so that it's not confusing with the variable being, the a and b being in the denominator, okay? And that's the domain of f of x, which should be -4 and 4 in our example here, right? So that means your a could be greater when you're dividing it by 2. You're dividing the x by 2, right? So because of this, the domain of f is stretched by 2 to create the domain of h. Okay, I hope that made sense. All right, so looking at the concept, stretches and compressions are multiplying by a factor of a. So vertical stretches and compressions, when a is greater than 1, then it's a stretch. When a is less than 1 but greater than 0, it's a compression. So we don't have negative numbers for vertical stretches and compressions or horizontal stretches and compressions. So for stretches and compressions, your factor that you're multiplying should be all positive, okay? Negative means different transformation. It means reflection. We looked at that, right? So yeah, negative is reflection. But the multiplication of a factor is always stretch and compression. So if you are multiplying by a negative number, then you have 2 transformations. So you should break that down into 2 parts. One should be a stretch or compression. The other should be a reflection. Okay? So again, horizontal stretches and compressions go the other way. So when a is greater than 1, it's actually a compression, horizontal compression. When a is less than 1 and greater than 0, then it's a horizontal stretch. So when a is greater than 1 in a fraction 1/a, that's another way to say a is greater than 0 and less than 1, okay? Yeah. All right, let's look at example 4 now. Graph a combination of transformations. What if we put all these together? We're going to start with f, okay? Using f of x, how can you graph a combination of transformations? So first of all, we want to graph y is equal to -f of x plus 2. How many transformations do you think we have? That negative is reflection. That plus 2 is a horizontal translation. So you want to do it one by one. So let's do translation first. We're going to go from inside out, okay? So from f, you are moving all your points to the left 2 units, okay? To the left 2 units. And then you're going to reflect this on the x-axis. How do you know if this is x or y-axis? Yeah, if the negative is outside and it's an opposite of the whole function, that means your y values are the opposites, right? Because in order to get y values, you're plugging in x to solve for the function, and that is your y value. So if you make your y value negative, that means your x is the same, your y values are being reflected on the other side of the x-axis. Okay, so yeah, if you look at the distances to the x-axis, you'll be able to graph all these reflective points. And so your h should be your final transformed function. Okay, so when you're graphing transformation, graph it one by one. Our part B, we're going to graph y is equal to 1 over 2 f of x plus 3. So now we also see two different transformations. That plus 3 is outside f of x, right? It's not inside the function. So that means we are changing our y, which is our vertical movement. So that's a vertical translation up 3 units, and that 1 over 2, that is a vertical compression because it's less than 1 and greater than 0, and it is multiplying by the function, right? So it's a vertical compression and a translation. So let's solve this one first and then go up 3 units. So the order of graphing is very similar to the order of operations. You're going to solve the parentheses, but in this case, it's a function notation. If there's anything inside a function notation, then you should do that first, and then you can do the other ones, okay? And in this case, we're gonna do multiplication first and then the addition. So we're going to vertically compress our f of x by changing our y values. So your x value stays the same, but then your y values are going to be divided by 2. So this becomes this, that 4 becomes 2, okay? So you just drop half. You're not subtracting the values, you're dividing it by 2, okay? So that would be your first transformation. And then from here, you're going to translate up 3 units. Okay, so from here, just go up 3 units. And that is your h. All right, so now it's your turn. Try number 4 using the graph of f above. So again, you can use the graph of f here. You're going to graph each function. Y is equal to f of 2x minus 4. Y is equal to f of 2x minus 3 minus 2. So pause the video and graph f, and then graph each transformation. Okay, are you ready? Okay, starting from f, your a was y equals f of 2x minus 4. So from here, let me write that down. Y equals f of 2x minus 4. So you're going to do a horizontal compression by 2, right? From all these points, you're going to divide your x by 2, your y stays the same. So negative 4 divided by 2, negative 2. So it's here. And then negative 2 divided by 2 is 1, negative 1. And then negative 1 divided by 2 is negative 1/2, and so on. So everything is 1/2 distance away from the y-axis, okay? So it should be like this. So this is your horizontal compression. It compressed horizontally. And then you will going to subtract 4. That is a vertical translation, 4 units on to the downwards, right? So then you're going to go 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. So your final graph should look something like this. So check if you have it correctly. All right. And then your part B, y is equal to f of 2x minus 3. That means you have a horizontal translation of 3 units to the right. And then you have horizontal compression of 1 over 2. Remember, your horizontal movements are opposites. And then your vertical translation of 2 units downwards. So we're going to graph all that, and if you graph all that, your final function should end up here. 1, 2, 3, and 2, comma 5. Yeah. Whoops. Okay, so check your answer and see if you got it correctly. Okay, we have examples 5 and 6 left. Let's continue in the next video.